Okay, so the question that I'll be explaining today is a question that says, which statements explain why catalyst is used in the contact process shown below? So you have an equilibrium reaction here. The first option states that the catalyst lowers the activation energy. A catalyst moves the position of the equilibrium towards the product. Catalyst allows the same rate to be achieved at a lower temperature. And we have different options to pick from to see which one of these three are correct. We either can pick 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3. Okay, so first of all, what we have to know is what is a contact process, or what is the collision theory. So, collision theory. The collision theory has three main laws, or three main rules that have to be ticked off, basically, in order for this for any collision to happen. So the first one is the obvious one. So the particles, they obviously must collide. And this one is a bit awkward because in order for any collision to happen, two particles or X amount of particles must collide in order for the collision to occur. So we'll just draw a simple diagram here. Just to compare it to other rules that are going to be said now. Now, the second rule states that the particles must collide with a certain orientation or geometry, and this will result in the reactive parts of the particles. They will basically come into contact with each other and form the reaction, or undergo a certain reaction. So the second rule is that must have a certain geometry, and this will give us reactive parts colliding between two particles. So we're just assuming two for now, just to keep the rules simple to understand. However, the third rule, finally, says that they must collide at a certain energy, a sufficient amount of energy, to basically trigger the reaction. Because if the energy is not met, activation energy in this case, then the reaction will not occur, because the activation energy is not met, obviously. So certain energy must be available, or must collide with sufficient energy. And with that being said, we now can draw the enthalpy versus time graph with the activation energy and the delta H. Okay, now just to draw the graph, we're going to have time as our x-axis, and we're going to have enthalpy as our y-axis. So now reactants are going to start here, about there, and the products are going to be low. And in this case, this is the an exothermic reaction, and when we draw the line or the curve, the line that separates the basically the line of reactants here, and to the maximum point of the graph. This is all the activation energy. Okay. However, the line that's between the reactants and the products is the enthalpy. And in this case, it is energy released, because it's an exothermic graph. And as I said, the activation energy is the minimum amount of energy required for any reaction to occur. So if that certain amount of energy is met, then the reaction will get begun, basically. Okay, and with that being said, there are factors that can actually make the reaction go faster, or lower the activation energy, hence making the reaction go faster. We have learned four factors that affect the rate of reaction. So the first one is temperature, second one is surface area, third one is concentration, fourth one is catalyst. Now I'll only be focusing towards temperature and catalyst, because it's focused in the question, and it actually states why a catalyst is used in this process. Okay, so now in general terms, temperature, so I'm talking about temperature now. If temperature increases, so increase in temperature equals more, so faster collisions, faster collisions, which means faster particles being collided, or the opposite actually, faster particles is equal to more collisions per time t. So actually in depth, as the temperature increases, as I said, the particles will move faster, so there will be more collisions per time t, or per second. But the main reason why an increase in temperature increases the rate of reaction is that more of the colliding particles here, more of them will have, if we increase the temperature, more of these particles will now have the necessary activation energy, which will result in more successful collisions to occur. So that's there. And now we could draw the graph, the general graph of having a higher temperature, and this is time, and this is volume of, let's say, x. So this is higher temperature, high T, and this is the lower temperature. So now going back to our question, or to the question, a catalyst allows, we could recognize the temperature is given in one of the options. A catalyst allows the same rate to be achieved at a lower temperature, and we saw that in the graph that I've just drawn, and in the explanation that I've just explained. And additionally, we also have a second graph in which energy and number of particles, so it's a number of particles versus energy graph, and this is going to be certain temperature this is going to be higher temperature. Now this part right here, this area under the curve, this means that more reactant particles will now have the necessary activation energy for the reaction to occur, which is what I just explained. And this line right here is high temperature. So we saw that the reaction went faster than the reaction here. It took way too long for it to go up and down, but this one went faster. So with that being said, we can conclude that 3 is one of the correct answers. Now let's look at catalysts and what they do to the rates. So what a catalyst does, so now we're talking about catalysts. They enter the reaction, but however they're not changed chemically, so they're not changed in their shape at the end of the reaction. What they do is that they bring the reactive parts, in which I explained at the beginning of the video, they bring the reactive parts of the reacted particles into cross contact with each other. And that was one of the rules of the corrosion theory that had to be ticked off. And in this case, it is ticked off. And this, and now generally a catalyst provides an alternative pathway for the reaction to take, and this alternative pathway withholds a lower activation energy. So a faster reaction will occur. As a result, more of the reactants will possess this lower activation energy, so the rate increases. And as I said, actually, similarly in temperature, the reactants will have will hold the necessary activation energy. More of the particles will now hold the necessary activation energy, lower activation energy actually, for the reaction to occur. And now we can also see that in the graph of enthalpy versus the reaction. So as I drew earlier in the beginning of the video of the exothermic reaction, so we're going to have reactants here, we're going to have products here, and that's the activation energy. Of the uncatalyzed reaction. Now, what happens if a catalyst were to be used in this reaction? There will be a lower line, which means, so let's say this was 100, for example, and this was 50. So the enthalpy changed, and it actually got decreased. And now the activation energy is lower, and this will go down to the products. And also, obviously, this section right here is the delta H. And now going back to the question 1, a catalyst lowers the activation energy. We just saw that being correct, yes. A catalyst moves the position of equilibrium towards the product. That is actually untrue, because, and now we could tick off A, C, and D, because we just did the process of elimination of 1 and 3 definitely being the answers. So the answer is B. Now let's look at why 2 is wrong. Why a catalyst moving the position of equilibrium towards the product is incorrect. Now, in general, the catalyst speeds up the forward and backwards, or the reverse reactions, to the same extent, basically, to the same point, or to the same line that's going to be reached by the catalyst. And because adding a catalyst doesn't really affect the rates of the two reactions, or actually in detail, the relative rates, because it decreases the activation energy but increases the rate. It can't affect the position of equilibrium. And basically for an equilibrium or a dynamic equilibrium, as we study in HL chapter 6 and 7, and by the way, this question is chapter 6 HL. So going back to my point, dynamic equilibrium, the rates of the forward reaction and the reverse reaction, they have to become equal. And obviously this takes time for this point to basically be ticked off or achieved. And for a slow reaction, I've done some research, and apparently it could take some years for it to happen in certain reactions. So, in conclusion, basically, a catalyst speeds up the rate at which a reaction reaches dynamic equilibrium. And that is why 2 is wrong, because it does not affect the position of equilibrium.